Hypothalamus Artificial Intelligence, HI, and Research Center for Advanced Decision Technologies, RCADT, presents the conference. Forecasting based on mathematical programming. Knowledge and not power, it is only potential. Appling that knowledge is power. Understanding why and when to apply that knowledge is wisdom. Takeda Shangen. System Advanced Analytics Model, SAAM. The Hypothalamus Artificial Intelligence, HI, has developed several of the models presented here as part of the SAAM system, which is based on mathematical programming. SAAM is mentioned several times. System Advanced Analytics Model, SAAM. Hypothalamus Artificial Intelligence, HI, has developed several of the models presented here as part of the SAAM system, which is based on mathematical programming. SAAM is mentioned several times. Advanced Probabilistic Models. Theory. Probabilistic models are crucial for enabling AI systems to handle real-world complexity and uncertainty. Unlike deterministic models that rely on predefined rules, probabilistic models can analyze probabilities and account for unpredictability. The total time is divided into three parts: training, validation, and prediction. The historical dataset is divided into two parts: training and validation, composed of training dataset, part of the historical sample used to train and calibrate the mathematical model, and test dataset, part of the historical sample that is not used to calibrate the model and is used to check the quality of the model. And the forecast period, in which the model will be used to predict new samples. Continuous dependent variable models. In probabilistic models there are three fundamental elements that must be modeled: probability distribution function average of processes, and variance, process standard deviation. The above elements can have dynamic behavior, that is, they may change over time. The Box-Jenkins methodology, by George Box and Willem Jenkins in 1976, is an iterative approach to time series analysis and prediction, using autoregressive integrated moving average, ARIMA, models. ARIMA and SARIMA are statistical models for time series prediction, where SARIMA is an extension of ARIMA that includes seasonality in the medium and long term. Both models use autoregressive, R, and moving average, MA, components, but while ARIMA focuses on non-seasonal data, SARIMA adds parameters to capture cyclical or seasonal patterns in the data. The GARCH model was developed by Tim Boleslav in 1986, generalizing the original ARCH model created in 1982 by the Nobel Prize Robert Engel. Boleslav introduced a more flexible model where variance depends not only on past squared errors but also on previous conditional variances. This extension allows the variance to depend on past square errors, providing a more flexible and practical structure. These models are useful for predicting future volatility. These models are supported by optimization methods that minimize the mean square error of the projected series for the observed values, commonly known as ordinary least squares, OLS. Under certain probabilistic hypotheses, OLS prediction parameters and errors can be associated with multivariate normal probability distribution functions, which coincide with maximum likelihood estimators, which maximize the sample probability function, and with the best linear unbiased estimators, blue. Multivariate regression, MR, relates independent variables to the variable in question, the dependent variable. For its application, the historical information of the dependent and independent variables is needed. To characterize probabilistically the behavior of the error term, homoscedasticity is assumed, which follows a normal distribution function with zero mean and constant variance, which is estimated in the process of parameter estimation, consuming a degree of freedom. The optimization models associated with M, R, are of the convex quadratic programming type. The autoregressive integrated moving average, ARIMA, identifies the type of stochastic process that generates the time series of a stationary dynamic variable without resorting to exogenous explanatory variables. It is based on a general formulation where lag p is the autoregressive component and q is the moving average component of stochastic errors. The ARIMA process is of the quadratic programming type with quadratic constraints. The combination of multivariate regression models with ARMA models, P, Q, gives rise to RMAX models, P, Q, that integrate the two types of models into an equation to explain the mean of the stochastic process of the dependent variable. The RMAX models, P, Q, are supported by the hypothesis of homoscedasticity of the error term, that is, its volatility is constant. They are solved by quadratic programming models with quadratic constraints. Homoscedasticity is the statistical property where the variance of the error terms in a regression model is constant across all values of the independent variable. Heteroscedasticity is the opposite, where the error variance changes, which can lead to biased and inefficient estimates in a model. A homoscedastic model is more reliable, while a heteroscedastic one requires further analysis or correction to ensure valid conclusions. The ARCH, autoregressive conditional heteroscedasticity, and GARCH, generalized autoregressive conditional heteroscedasticity, family of models emerged after the ARIMA models. The ARCH model is the first method to determine a dynamic behavior for variance, modeling it as a dependent variable based on the past values of the variable itself, and on the exogenous variables included in the model. High-frequency time series, such as daily, hourly, are characterized by being asymmetric, leptokurtopic, clustered and with a high persistence in volatility, with correlations in squares, leverage effect. This mainly applies to the series observed in the financial and foreign exchange markets. To collect these characteristics, a series of nonlinear models have been proposed, among which the models of the ARCH family stand out, whose main objective is to relax the hypothesis of homoscedasticity, allowing variability over time. The generalization of the models ARIMA and GAR that gives rise to the model family RMAX-GARCH, autoregressive moving average model with exogenous variables and generalized autoregressive conditional heteroscedasticity, in which RMAX models are integrated with GARCH. Conventionally, GARCH models and their extensions are estimated by the maximum likelihood method, which requires assumptions about the behavior of the error. However, under normality hypotheses, the estimation process can be performed under a nonlinear least squares approach, the latter because the errors are estimated as part of the basic model. There are many variations in the GARCH model that differ in the hypotheses of variance modeling. The leverage effect in GARCH models is sometimes described as the term threshold in CARC models and refers to the asymmetry in which negative news increases volatility, while positive news reduces it, something that standard GARCH models do not capture. The nonlinear relationships between the dependent variable and the independent variables can be handled with kernel functions. System Advanced Analytics Model, SAAM. The Hypothalamus Artificial Intelligence, HI, has developed several of the models presented here as part of the SAAM system, which is based on mathematical programming. SAAM is mentioned several times. SAAM can manage the combination of models that facilitate the overall estimation process of an integrated statistical model that includes steps with multiple simple models. For the analysis of continuous variables, SAAM is based on a generic model that allows the user to configure multiple specific models according to the particularities of the random processes that affect the representative variables of the system under study. The statistical indicators used to generate the prediction are mean and variance. To model the mean, the following methodologies are used. Multivariate regression and autoregressive and moving average seasonal models, SREMA. To variance, GARCH, generalized autoregressive conditional heteroscedasticity, models are used. For the analysis of continuous variables, SAAM is based on a generic model that allows the user to configure multiple specific models according to the particularities of the random processes that affect the representative variables of the system under study. The statistical indicators used to generate the prediction are mean and variance. To model the mean, the following methodologies are used. Multivariate regression and autoregressive and moving average seasonal models, SREMA. To variance, GARCH, generalized autoregressive conditional heteroscedasticity, models are used. For the analysis of continuous variables, SAAM is based on a generic model that allows the user to configure multiple specific models according to the particularities of the random processes that affect the representative variables of the system under study. The statistical indicators used to generate the prediction are mean and variance. To model the mean, the following methodologies are used. Multivariate regression and autoregressive and moving average seasonal models, SREMA. To variance, GARCH, generalized autoregressive conditional heteroscedasticity, models are used. For the analysis of continuous variables, SAAM is based on a generic model that allows the user to configure multiple specific models according to the particularities of the random processes that affect the representative variables of the system under study. The statistical indicators used to generate the prediction are mean and variance. To model the mean, the following methodologies are used. Multivariate regression and autoregressive and moving average seasonal models, SREMA. To variance, GARCH, generalized autoregressive conditional heteroscedasticity, models are used. The ordinary least squares, OLS, model shows the change in volatility at the indicated point. To improve the situation, a weighted least squares model, WLS, is subsequently run, which weights errors according to the OLS results. For the analysis of continuous variables, SAAM is based on a generic model that allows the user to configure multiple specific models according to the particularities of the random processes that affect the representative variables of the system under study. The statistical indicators used to generate the prediction are mean and variance. To model the mean, the following methodologies are used. Multivariate regression and autoregressive and moving average seasonal models, SREMA. To variance, GARCH, generalized autoregressive conditional heteroscedasticity, models are used. To use the maximum likelihood method, it is necessary to assume a probability distribution function for the sample, and the method will be responsible for estimating the optimal parameters. The classic thing is to assume functions of normal distribution, which is equivalent to minimizing the sum of the squares of the errors. But it is also possible to test various probability distribution functions that produce different indicators of maximum likelihood and different shapes of the estimated curves, being able to compare and observe the results they produce. To implement the method based on mathematical programming, what must be done is to implement a nonlinear problem, which reflects the chosen distribution function in the objective function. Two-stage least squares, 2SLS, are a case of parameter estimation in two stages. Parameters are estimated based on the ordinary least squares, OLS, method. The parameters are estimated by weighted least squared means, WLS, using as a weighting factor the inverses of the coefficients of the covariance matrix of the errors of the OLS model. Parameter adjustment can be done using linear functions. The cases are: minimize the sum of the absolute value. The parameters are determined by minimizing the sum of the absolute value of the estimation errors, and minimize maximum error. Parameters are determined by minimizing the absolute value of the maximum estimation error. These processes give rise to a linear programming model. Generalized support vector regression. In 1997, Drucker et al., in the article Support Vector Regression Machines proposed vector support machines, SVM, for the regression problem. The objective is to build a margin of tolerance with which observations will be made within the margins and outside the margins. Using only the observations outside the margins, the errors are calculated and with them the objective function to be minimized is constructed. Generalized support vector regression, GSVR, is not a single, standard algorithm. The term refers to improved versions of the traditional support vector regression, SVR, algorithm. These generalizations incorporate regularization techniques, and/or advanced parameter selection methods to improve performance on certain specific types of data. According to the principles of support vectors, GSVR can be formulated including the concepts of statistical regression, kernel functions and vector support machines. To this end, it is proposed to solve a prediction error minimization model for which an insensitive zone is established in which prediction errors are not considered in the penalty function. The model to be solved is a mathematical programming model. From the point of view of optimization for parameter identification, the difference between support vector regression, SVR, and ordinary least squares, OLS, is that when the error is equal to 0 and p is equal to 2, the mathematical problem to be solved is equal. This implies that SVR allows an insensitive zone of size below which small errors are ignored, which gives greater importance to large errors. This means that large errors decrease, increasing the value of small errors in the insensitive zone. The image shows the difference between OLS and SVR. Those who are interested can watch the following video or a similar one. Bender's decomposition for support vector regression. The document Bender's decomposition technique for support vector regression proposes to apply the Bender's decomposition technique to the resulting LP for the case of support vector regression. In 2022, the results show that this technique is much faster than the quadratic formulation. The document Bender's decomposition technique for support vector regression proposes to apply the Bender's decomposition technique to the resulting LP for the case of support vector regression. In 2022, the results show that this technique is much faster than the quadratic formulation. The image presents the algebraic formulation of the monolithic problem. The image presents the algebraic formulation of the Bender's decomposition problem. The image presents the algorithm implemented for the Bender's decomposition problem. The speed ratio compared to Bender's is 1 to 2.95 for linear programming, and 1 to 60 for quadratic programming. This demonstrates the benefit of large-scale mathematical optimization techniques. As it can be seen in the table, when the sample size grows, the time to solve the quadratic programming increases exponentially. Discrete dependent variable models. Discrete dependent variables. In statistics, binomial regression is used to model a binary dependent variable, 0 or 1. There are at least 3 methodologies to deal with the problem: discriminant analysis, logistic regression, and probit model. These models maximize the likelihood of the sample, maximum likelihood, and differ in their probabilistic assumptions. Logistic regression. Logistic regression is a statistical and machine learning technique used to model the probability of a binary outcome, such as an event with only 2 possible outcomes, yes or no, or 0 or 1. It works by analyzing the relationship between one or more predictor variables and the outcome, adjusting a sigmoid function to predict the probability of the outcome occurring. For example, it can be used to predict the probability of failure in a cable segment, based on the cable's age of operation. The logistic regression classification approach was applied to an urban distribution system in Western Canada. The studies included 1,000 single-phase cable segments recorded over 5 years, between 2012 and 2017. The data was divided into a training and a test set based on an 80-20 ratio. The test suite was used to evaluate the performance of the model. The trained model is shown in the figure. The mesh surface indicates the logistic regression value for any pair of physical and conditional ages. The red and green dots represent the failed and functional cable segments. The confusion matrix, the accuracy index, the recall index and the F1 score were used for the evaluation. These indices can describe how well the model classifies or predicts 2 states separately. The confusion matrix is shown in the table. The acronyms TP, FP, TN, and FN stand for true positive, true negative, and false negative counts. Demand forecasting with artificial intelligence. Data input modeling. Forecasting aggregate demand in a sector, area, manufacturer, category, and/or channel, or combinations of the above, has 2 alternatives. Bottom up. The projection of aggregate demand is made at the lowest level of the grouping, at the level of the atom, which implies having the capacity, data and computing power, To estimate a statistical model for each demand series, product, point of sale, POS. Atoms relate to SKUs at a point of sale for a day. Top-down. The projection is made at the level of aggregate demand, and then it is disaggregated at the level of atoms, for which it is required to have disaggregation rules, which are generally not self-evident, and therefore they are rules of thumb. If possible, Hy prefers the bottom-up method. From the point of view of the volatility of the data series, and therefore of the projections, volatility is expected to decrease at the aggregate level. However, the above is true if the demand correlation in atoms tend to have neutral or negative correlations. If the correlation is positive, the volatility of aggregate demand will be higher. The first step in structuring a demand model is to select the type of statistical model to use. The first models available were self-explanatory models based on time series of the Box and Jenkins type. The current models are exogenous models combined with self-explanatory models, based on the theories of Box and Jenkins, complemented by GARCH models, and including exogenous variables. The generalized autoregressive conditional heteroscedasticity, GARCH, model, is a statistical technique used to analyze time series data, if the variance of the error term, or the difference between the actual and predicted values, is serial autocorrelated. The demand for products, and/or services, is the result of the integrated impact of multiple factors. These can be grouped into economikos, prices, product and point of sale attributes, competitor activities, advertising, and seasonality of multiple kinds. This implies that a demand model that only considers consumption time series, and possibly sales prices, leaves out important effects that affect demand. For this reason, models based on simple time series, such as Box and Jenkins, need to be expanded to consider all the effects. The two main results of the DEM model are characterization of the competition, and characterization of the client. This is summarized in algebraic equations, which characterize the mean and the variance of the demand process, so that the characterization is probabilistic. To estimate all the impacts, more specifically the elasticities of demand with respect to the factors, it is necessary to add databases from different sources to the company's databases, depending on the type of market. As an example, the image presents information from the following types of databases: historical sales information, hydroclimatic databases, socio-demographic information, Nielsen, syndicated database, history of promotions, own and competitors, and seasonal events. Effects included. The model must allow the inclusion of different types of elements, to represent processes of demand for goods and/or services with very different behaviors. In DEM, the generic equation to explain the average demand is made up of the following additive components: elasticity of demand versus price, cannibalization, pantry loading, lost sales, time trend, periodic seasonalities, seasonalities of events or business initiatives, effects of global exogenous variables, effects of regional exogenous variables, autoregressive effects, moving average effects, product attribute effects, POS attribute effects, and zone attribute effects. With proper modeling, it is possible to decompose demand as the sum of the impact of the different factors. This applies to every product, every point of sale, and every period. For example, the demand may be broken down into base demand, competitor pricing and promotions policies, product features, seasonality, and company marketing policies. The elasticities of factors, which are under the control of the company, are essential to optimize the marketing mix and market share, and others' marketing and sales decisions of the company. This implies that the process of sampling events, and in general the collection of information, must consider the activities that are planned to be carried out in the future. Therefore, the demand model aims to answer the main questions about market behavior. HiDem provides quantitative answers to questions such as: what is the immediate effect of marketing mix decisions, e.g., 2-for-1 promotions, space events, advertising investment, etc.? What is the impact of periodic events on demand, e.g., end of month, fortnight, Easter, day of the week, etc.? What is the impact of promotions in later periods? What is the effect of product features, e.g., colors, textures, etc.? What is the effect of point-of-sale features, e.g., size of the premises, floor, etc.? What is the natural level of growth in demand, without considering seasonality or marketing events? What is the impact of exogenous variables, such as climate, national GDP, or regional GDP, or population? What is the demand-price elasticity of each reference? And does this elasticity behave seasonally? It is a question of individualizing demand in all its components. It corresponds to a proactive position of the seller in which, based on artificial intelligence models, the seller tries to influence buyers to make their purchases in response to the seller's actions. Some examples: targeted offers at the time of accessing a website, selection of the days on which the beer festivals will be held, determination of campaigns in the advertising media, choice of marketing campaigns according to the points of sale, and definition of prices according to the points of sale, the times of the day, and/or the events that occur, among many. The flow of the analytical process is data cleansing, prediction model, forecasting, selection of control variables, and optimization model. In a traditional approach, the control variables are defined by the decision makers, based on their mental model, and therefore, directly or indirectly, are input data to the optimization model. HiDem provides quantitative answers to questions such as: what is the immediate effect of marketing mix decisions, e.g., 2-for-1 promotions, space events, advertising investment, etc.? What is the impact of periodic events on demand, e.g., end of month, fortnight, Easter, day of the week, etc.? What is the impact of promotions in later periods? What is the effect of product features, e.g., colors, textures, etc.? What is the effect of point-of-sale features, e.g., size of the premises, floor, etc.? What is the natural level of growth in demand, without considering seasonality or marketing events? What is the impact of exogenous variables, such as climate, national GDP, or regional GDP, or population? What is the demand-price elasticity of each reference? And does this elasticity behave seasonally? It is a question of individualizing demand in all its components. Bayesian ensemble of models. In simple words, the fundamental model predicts the next word in a sequence. GPT models are based on the knowledge they acquire after being trained on hundreds of billions of parameters in huge linguistic datasets. In the 18th century, Thomas Bayes can be credited with the first GPT model, when he explicitly used the chain of Bayes' theorem to predict strings of text in a similar way to how GPT does today. The text presents the summary of the life of the scientist Thomas Bayes. Current artificial intelligence is based on generative pre-trained transformers, commonly known as GPTs, which are a family of neural network models that allow you to create images of text and content, music, and more, like how a human would and answer questions conversationally. GPT models are described as artificial intelligence, but this is an overview. More specifically, GPT models are linguistic prediction models based on neural networks and built on the transformer architecture. They analyze natural language queries, known as prompts, and predict the best possible response based on their understanding of the language. In simple words, the fundamental model predicts the next word in a sequence. GPT models are based on the knowledge they acquire after being trained on hundreds of billions of parameters in huge linguistic datasets. Meta-algorithms to combine multiple identification algorithms are based on the probabilistic combination of models using Bayes' theorem as support. The result is a combined model resulting from the weighting of several models, whose weights come from the a posteriori probability that each model is the true model. The mathematical methodologies used are Bayesian combination. Bayesian inference is a method based on Bayes' theorem that is used to update the probability of a hypothesis by considering the information that is acquired because of an event. As more evidence or information available, Bayesian inference has found application in a wide range of activities, including science, engineering, philosophy, medicine, sport, and law. Bayes' theorem solves the problem known as inverse probability. That is, to probabilistically evaluate the possible conditions that govern the event that has been observed. The followers of Bayesian inference claim that the transcendence of inverse probability lies in the fact that it is the one that really interests science, since it tries to draw general conclusions, enunciated laws, from what is observed objectively, and not the other way around. Bayes' theorem expresses the conditional probability of a given random event A in terms of the conditional probability distribution of a given event B A and the marginal probability distribution of only A. Mathematically it is formulated as A1, A2, A3, A, T, a set of mutually exclusive and collectively exhaustive events, such that the probability of each of them is different from 0, 0, and let B be any event for which the conditional probabilities of B are known given an event AI. Then, the conditional probability of an event AI given event B can be calculated. The Bayesian approach is particularly important in the dynamic analysis of a data stream, and by itself involves a process of learning from the data. It is the case of the prediction of the ENSO, El Niño Southern Oscillation, phenomenon which the International Research Institute for Climate and Society of Columbia University, IRI, which uses two types of models for the prediction of ENSO. IRI publishes results of two methodologies for projections of models combining subjective based on a consensus among analysts of the CPC, Climate Prediction Center, and IRI. Objective based on a mathematical model that determines the weighting factors of each of the models available based on the results obtained in the last periods based on a combination of Bayesian model. The benefits of this approach are discrimination of a model such as the real model, the most probable, composition of a general model based on the weighting of different models, using its probability to be the true model. This dynamic selection of the structure of the model implies a learning process. State estimation and Kalman filter. Rudy, Emil Kalman was a Hungarian-born American electrical engineer, mathematician, and inventor. Rudolf Kalman was born in Budapest in 1930. Kalman was most noted for his co-invention and development of the Kalman filter, a mathematical algorithm that is widely used in signal processing, control systems, and guidance, navigation and control. For this work, U.S. President Barack Obama awarded Kalman the National Medal of Science on October 7, 2009. Kalman's work is based on Bayesian modeling. The approach for the state estimation, SC, is supported on a conception of the stochastic processes, where the random variables are clearly differentiated of the measures, being understood that the modeler has data of the measurement system, that may be different from real values of the random variables. Therefore, all available observations are considered as random variables, having their measure information, but which, by reason of the randomness of the measuring system, are subject of precision errors, therefore, assume them as deterministic induces errors. Moreover, there might be more than one measure for a random variable, obtained by different sources. Two types of noise, or errors, are considered in state estimation modeling. Two types of noise, or errors, are considered in state estimation modeling. Errors due to the modeling of the system, reflecting the uncertainty of knowledge of functions, equations and/or parameters, that determine the behavior of the system that is modeling, and measurement errors that come from the precision with which the random variables associated with the system are measured. The conventional statistical models only consider one type of error, which integrates modeling errors and measurement, whereas the state estimation modeling differs clearly the two types of errors. The state estimate describes the system based on state variables, characterized by discrete, empirical probability distributions, and dynamic, empirical, probability distribution functions that evolve over time. Mathematical formulation of Kalman filter. It is made up of two equations. Equation of state, where the following definitions are met. System state vector transition matrix control vector control interaction matrix noise vector and modeling noise interaction matrix. The above equation can be approximated by differential equations, or by finite difference equations. The KF process has as its starting point the dynamic equation of state variables, which has as its input the a posteriori prediction in t-1, and the control variables in t. The result is the a priori estimate of the state variables for period t. Using the observation equation, KF produces the a posteriori estimation of the vector of measures zt. On the other hand, the system that is being observed, through the measurement system, produces the actual measurements. The comparison between the estimate a priori of zt and the real value of zt produces an error, or innovation, that is used to make corrections in the state variables. This is done by means of the so-called gain matrix, M, which is a central part of the KF. The result is the a posterior estimation of xt, which will be the starting point to carry out the process in the next period, t plus 1. We ignore the past as much as the future. Of the present we generally ignore where we are. The stochastic processes where the random variables are clearly differentiated of them measures allow the modeler to improve knowledge of the past based on the evidence of the present. It can only be realized by a combination of forward and backward processes. If T1 is the period for which you want to obtain the best estimator of the state variables, given the information received up to T. The relationship between T1 and T defines several types of process. Smoothing, T1 less than T, it involves predicting a posteriori the state variable in the past T1, before T. Filtering, T1 equals T, it involves the correction, filter, of the prediction of the state variables in T, while reaches the information. Forecasting, T1 greater than T, it involves the prediction of the state variables for periods T1 after the present T. The last two functions are the most used, however, the prediction of the past makes perfect sense when we recognize that in the past, we only had estimates of the state variable, because we never know its real value, which can be improved by processing the information coming later to T1. State estimation models assume that we ignore the past almost as much as the future, and for the present we have a rough idea of where we are. As we acquire information, uncertainty in all directions must decrease. Markov decision process. Today, in artificial intelligence, it is the mathematical framework that underpins reinforcement learning, RL, that models an agent's sequential decision-making in a stochastic environment to maximize accrued rewards. According to Markov property, the future state depends only on the current state and action, not on the whole story. RL algorithms find an optimal policy, what to do in each state by learning from the states, actions, and rewards. The MDP is well understood when the state and the spaces for action are small. Bertskas, 2007, and dynamic programming, PD, algorithms, such as value iteration, Bellman, 1957, and policy iteration, Howard, 1960, are standard techniques for calculating optimal policies. In large state space problems, exact DP is not feasible since computational complexity scales quadratically with the number of states. The text presents the summary of the life of the Russian scientist Andrei Andreevich Markov. His best-known contribution is theoretical work in the field of stochastic processes known as Markov chains, which today are considered an essential tool in disciplines such as economics, engineering, operations research, and many others. In probability theory and statistics, a Markov process is a time-dependent random phenomenon for which a specific property is fulfilled. The Markov property, or without memory, is one for which the conditional probability about the present, future, and past state of the system is independent. The most practical importance is the use of the assumption that the Markov property is valid to construct a stochastic model for this process. It is a simple way to introduce statistical dependence, in such a way that it allows the strength of the dependence of the different delays to decrease as the delay increases. The term Markov chain is often used to imply that a Markov process has a discrete state space, infinite or countable. Normally, a Markov string would be defined for a discrete set of periods, such as a discrete time Markov chain, although some authors use the same terminology where time can take continuous values. We can talk about different definitions about the first-order Markov processes. States, the conditions in which an entity or possible events are found. Trials, repeated occurrences of an event being studied. Transition probability, the probability of moving from state I to state J in a transition or period. Markov, first-order, processes, to be used as models of physical or economic processes, must have a series of characteristics. The probability complies with the Markov principle. Existence of a finite number of states. The probability must be constant with respect to time or period. The trials must be in equal periods. The diagram presents two cases of simple Markov chains, one describing customers in a market and one describing the evolution of the climate. Transitions indicate that the probability of migrating from one state to another is independent of states and transitions between states. The transition matrix must be estimated from the historical sample, which can be done with a mathematical programming model. The long-term study facilitates the understanding of the behavior of the system. In this case, the chain has two entrapment states, 7 and 8, which implies that in the end the system will end up in one of those two states. The estimation of the matrices of a Markov process can be done using a mathematical programming model. In the case that they are considered dynamic, a Bayesian inference model can be used. The key components of an MDP are states, the different situations the environment can be in, e.g., a robot's location, a game's board configuration. Actions, the choices the agent can make in each state, such as move north, east, south, west. Transition probabilities, the probability of moving from one state to another after taking a specific action, incorporating randomness. Rewards, the immediate feedback, positive or negative, received after an action, guiding the agent toward its goals. Policy, a strategy or rule that dictates which action to take in each state to achieve the objective. The diagram shows an example of a simple Markov chain decision process, MDP, with 3 states, green circles, and 2 actions, orange circles, with 2 rewards, orange arrows. Markov decision processes are controlled Markov chains along with an immediate cost function and optimization criterion. The image presents the summary formulation of linear programming to solve MDP. Kalman's theory of filters has been extended to consider the modeling of systems whose dynamic representation depends on the state or regime in which the system is located. In this case, the regime in which the system is located should be considered as an additional state variable that must be estimated online, as it can be constantly changing. Examples of the state of a system can be: in a person, good temper, bad temper, calm. In a basin, dry, wet, is its transition. In a customer, happy, dissatisfied. There are countless examples that can be cited. In all of them, it has been proven that the response of the system, person, basin, client, etc., can respond to stimuli from the environment depending on the state in which it is, which in many cases is not fully identified. Thus, the concept of states can be associated with a semi-Markovian process, time-dependent transition matrices, in which a system can be found, with probability of transition from one state to another in any length interval delta t, which is not stationary and can change as the process develops over time. The regimen is an additional state variable that MSKF must estimate. Consider that a system could be in one of three regimes. Stable, the system does not change while maintaining the state it is in. Structural transient, the system is in a process of change between two states, maintaining this situation until the change of structure is completed. Stochastic transient, the system receives a stochastic impact that affects the state estimate but does not change the balance. The dynamics of system change is determined by a Markovian system in which the a priori probability of transitions between states is known. The Kalman filter is responsible for estimating the a posteriori probability, based on what it observes. In this example, to determine the states, the covariances of stationary parameters, dynamic parameters and observations are characterized. When the state of the system is stationary, all covariances are normal. If a transient structural change is detected, it is because the covariances of the dynamic parameters are large and can enter a process of change. If the process is stochastic transient, it is because the covariances of the observations are large. MS_KF is responsible for determining which are the valid covariances, through a process of weighting a posteriori. This modeling can be modified according to the criteria of the mathematical modeler. The multi-state Kalman filter was applied for the first time in 1978, to predict the flow of the Caroni River in Venezuela, with an average of 5,000 cubic meters per second. The table presents the aggregate results of the project, according to statistics from the World Meteorological Organization, WMO. Operational efficiency. It is the study of the operational efficiency of decision-making units, DMUs, of a system. Examples of DMUs are bank branches, soccer players, ATMs, departments, production plants, in general, any entity included in a production process. Operational efficiency can answer the following questions. Identification of anomalous, strange, or interesting DMUs, outliers, ordering of DMUs according to a measure of efficiency. Efficient production frontiers as a function of the resources used and the products produced. The mathematical methodologies used are: Data envelopment analysis, DEA, is a non-parametric, based on observed data, method for estimating Pareto production frontiers. It is used to empirically measure the productive efficiency of DMUs. It corresponds to a mathematical programming model. Stochastic frontier analysis, SFA. It is a parametric method, based on a hypothetical mathematical function, to identify economic models of production. The most widely used production function in economics is the Cobb-Douglas function. It is solved based on a process of advanced probabilistic models. The description below is taken from the work of Sellers, Nicolau and Moss, 2002. In the field of economics, efficiency refers to a judgment about the relationship between the means used and the ends obtained, Bosch, Pedraza, and Suarez, 1998. A technique, a process, a person or a production system will be efficient if, given a given availability of inputs, it is able to produce the maximum number of outputs possible or, alternatively, if it uses the least number of inputs to achieve a certain level of outputs. The organizational unit, hereinafter DMUs, decision-making unit, for which we want to measure its efficiency can be of several types: productive units within an organization, companies or companies within a sector, people/projects within an organization. For the estimation of contour functions, two basic types of models have been proposed, parametric and non-parametric. The difference between the two is that the former specify a functional relationship between inputs and outputs, while the latter impose no relationship at all. The advantage of parametric method is that, if the limit is correctly defined, there are greater guarantees that what is being identified as inefficiency is so. As a disadvantage, they present the need to specify a certain production technology that, a priori, may be unknown. In addition, it does not allow simple analysis of production processes with more than one output. The best known is the so-called stochastic boundary analysis, SFA. On the other hand, the main advantage of non-parametric models is that they do not require the specification of a production technology, since the efficient frontier is built from the observations existing. The best known of the non-parametric methods is the data envelopment analysis, DEA. Data envelopment analysis. The DEA, Data Envelopment Analysis, was developed by Charnes, Cooper and Rhodes in 1978, Charnes et al., 1978, and has been used to estimate the efficiencies of DMUs in various fields of application, as can be seen in the work published by Cooper et al. In 1999. DEA is an efficiency measurement model, supported by mathematical programming techniques that aims to evaluate the relative efficiency of different homogeneous DMUs. The application of a specific model for each DMU allows us to obtain a measure of efficiency for each DMU. The basic idea is to determine the relative efficiency of DMU from the analysis of data samples from multiple DMUs that can be comparable. To analyze the efficiency of a particular DMU, it is considered relatively efficient if no other DMU can produce a higher level of outputs using the same inputs, or produce the same level of output from a lower level of inputs. Thus, it will be possible to distinguish in principle those units that behave efficiently from those that are not, so that efficient units define an efficient limit, which corresponds to the smallest convex envelope, convex hull, that contains all the data of the DMUs. The DMUs that remain in the envelope are efficient in the sense that there is no real experience that indicates that for a given consumption a higher production can be obtained. The L5, L6 and L7 DMUs are inefficient since visually better possibilities of use of the resources of these DMUs are identified. For example, the area limited by the red lines implies possibilities for better use of the resources, inputs, used by the L5 DMU. Charnes propose an input-oriented model, with constant returns to scale, called CRS, constant return to scale, that considers that if a DMU H uses an input and produces an output, the relative efficiency of the DMU consists of calculating the quotients that measure the input-output ratio. The most efficient DMU H will be the one that maximizes the previous value. However, DMUs use multiple inputs to simultaneously obtain multiple outputs. In this case, there is a problem associated with the definition of the efficiency measure, given the lack of dimensional homogeneity of the different products and inputs. The problem can be solved by introducing a system of appropriate weights that normalizes both the numerator and the denominator. Stochastic Frontier Analysis. Stochastic Frontier Analysis, SFA, is a parametric methodology for the economic modeling of efficiency that considers the efficient frontier as a parametric function based on the technological characteristics of the production process. It is a matter of estimating the production function and its parameters based on observations existing. Typically, the functional form is based on Cobb-Douglas production functions or similar. SFA has its starting point in the models introduced simultaneously by Einer, Lovell and Schmidt, 1977, and Mayusin and van den Broek, 1977, propose the following model. If there is a sample of inputs and outputs from several DMUs, it is possible to determine an efficient limit by means of a regression approach based on ordinary least squares, OLS, by determining the prediction errors, solving the SFA OLS problem. The previous SFA consider a production system where Y represents production and there is a single input, X, which represents the cost defined as the production function. From the OLS line it is possible to determine the most efficient DMU as the one that establishes the lowest cost to produce a unit of Y, which would correspond to point A. In general, the most efficient DMU, A, is determined to have the highest negative error in the sense of efficiency. From the above information it is possible to obtain the limit of an efficient limit that passes through the point YAXA and has the same functional form. This method is called corrected least squares, COLS, associated with the SFA calls. The biggest drawback is that deviations from the efficient frontier are attributed to inefficiencies, but some differences may be due to data and measurement errors. Therefore, this deterministic limit is very sensitive to special observations that have a disproportionate effect on determining the value of the estimated parameters. This can be solved by including stochastic models in the analysis. This issue is not addressed in this document. SFA models can be solved with OLS and/or GSVR models. Like Herbert Simon, Hypothalamus Artificial Intelligence believes that the computer-based mathematical modeling is the greatest invention of all times. Thank you for your attention.